What really happens when we visit a website? Well, a lot, turns out, actually. And before we begin, just make sure we have the HTTP plus analysis PCAP open. So, the internet really is just an endless sea of client requests to servers, and servers responding with what the client asked for if they're authorized to view it. And really, in a nutshell, that's kind of it. And two major components in that are the three-way handshake and the client-server model. So let's see what those are. Let's start off by looking at the first three packets in action here. And in packet number 1, first we'll see that a DNS request takes place with the client-server model fully in display here, really, showing that the source is us acting as the client and the destination is the DNS server making a DNS request for the A record of demo.redmine.org. And that's just by looking at the packet list pane. Let's open up the DNS header, and we can see that information here. If we look inside of the queries header, we can see that a request for the A record of demo.redmine.org was requested. Cool, so now let's look at packet number 2. So this is the DNS response in action. And we'll go and expand the answers header to see what the response was. So we can see that it actually provides an IP address of 46.4.36.71 as the response to asking what the A record was. And that's an example of the client-server model in action. We have us as the client requesting to the DNS server for the IP address by getting the A record of demo.redmine.org, and the DNS server then responded back to us as the client and said, hey, the IP address that you're looking for is 46.4.36.71. Now let's look at packet number 3. And this will also demonstrate the client-server model in action, but with the HTTP protocol. And this one gets a little bit more convoluted because HTTP is involved and thus the three-way handshake becomes part of it. So what we're seeing here is that the source, which is us, now performs an HTTP GET request to the IP address that we just received from our DNS server. This is demonstrated inside of the IPv4 header. As we can see, the destination address of 46.4.36.71 was requested. Now expanding the hypertext transfer protocol for HTTP, we can see the GET request was requested to that destination address. And if you notice at the number column in the packet list pane where it starts at number 3, you can actually see an arrow linked all the way down to packet number 6. And this demonstrates to us that these packets from 3, 4, 5, and 6 are actually all linked together from one request. And if we select packet 4, we can see that inside of the HTTP header in the bottom, it's just more continued data from the initial request of packet number 3. And then finally in packet 5, this is the true destination of the initial GET request, that it's taking us to an account register page. And then looking at packet 6, the final request in the sequence, we actually have an interesting error over here, suggesting that the TCP previous segment was not captured. And this can happen. We don't see this when we're browsing websites, but there are a lot of general errors that occur. And in this case, this is one of them. It's suggesting that there was some type of congestion or some type of error that occurred in the sequence of requests and that there might be some missing information along the way. But it's course corrected itself and it did complete the request, so we're safe to say that this is okay. And so these packets from 3 to 6 demonstrate the client-server model again in action. We had a ping-pong request back and forth from us as the client requesting to the destination IP that we got from the DNS request. We then requested some HTTP data, the server accepted it, sent it back, and then we requested a little bit more to get to the account register page. The server accepted it once again and sent it back to us. And that's really it. It just keeps kind of ping-ponging back and forth this way. And then finally, looking at packet 7 and 8, we can see a post request happening, and that's an HTTP post request. And this means that we've now submitted data to the server as opposed to requesting data. And in this case, that's us logging in. And we'll look later towards the end of the lab what's actually happening here inside of the stream. But this is HTTP and not HTTPS, meaning that it's not encrypted. And this is why we haven't seen that three-way handshake yet that we're going to talk about. Is in this case, we just strictly have a client-server model request and response happening, and nothing's encrypted. So let's now actually move over to packet number 9, and it's here that we'll actually see encryption start to happen with an HTTPS request. So in packet 9, we're back in DNS. We had our client request youtube.com, the type A record, and now moving over to packet number 12, We see a response from the DNS server, and it's providing us an IP address, several of them actually. And the first one is now giving a response back of 172.253.63.91. So the same thing will happen like we saw earlier. Now that we have an IP address, our client can make the request to that IP address that it was given. It's all really simple stuff, just happening super fast. Now let's look at packet 19. We're finally here now, and this is the start of what's called the three-way handshake. This is a series of client-server requests and responses happening, whereby a trusted HTTPS session is created. And this is why you can log into your bank online and why it's fully encrypted, and that no one else can read it. Let's expand that TCP header inside packet 19, and then the flags header within inside of it. And here we can see all the TCP flags being set at the start of the initiation of the three-way handshake. What we can see here is the SYN flag being set inside of this TCP request, and this is for synchronize. This is where the client sends a sequence number to the server, and the sequence number can be observed here. It's right over here starting with 112. This is the number that will be sent over to the server to begin the process. Now let's select packet 20, and this is the second step. This is the server now responding, and it has the TCP flag set of SYN and ACK. So it's synchronizing and acknowledging the initial synchronized request from the client. And that's not all. It's actually responding with an acknowledgement number. And the acknowledgement number is actually the initial sequence number incremented by 1. And the server also has a sequence number that it gives back to the client. It starts over here with 127. And finally, we move over to packet 21, which is the final packet in the three-way handshake. And we can see that the client now has sent an ACK flag back to acknowledge, and along with the acknowledgement, the client sends back a request with the acknowledgement number that the server sent it, but also incremented by 1. And now that both parties have agreed on starting sequences of numbers that they can both increment by 1, they can move on to the encryption process where keys are exchanged. And each of these requests following forward where the keys are exchanged will carry on incrementing the sequence numbers. If those numbers get out of sequence, then we know that the connection is bad. Okay, now we can move over to packet 22 with the client hello. So let's close up the headers in the packet details pane, and then open up the transport layer security header so we can examine what's happening here. Expand the TLS version 1.3 header and then the Handshake protocol header. And in here we can see the client is offering under the cipher suites header all the encryption cipher suites that it's capable of working with. And it's going to just bundle this up and send it over to the server and say, hey, I can work with any one of these. What can you work with? So then we move over to packet 24. And this is the server saying hello back. And the server says, hey, you know what? I can actually work with a cipher suite that you have. And I'm going to offer we work with TLS AES 128 GCM because that's the strongest cipher suite that we can both agree upon. Along with this agreement acknowledgement, the server will also send its digital certificate. And inside of that certificate is included the public key, hence the key share process has begun. And now a series of ping pong requests are going to occur. What will happen is the client will take the public key and generate a pre-master secret or a secret key, and then it'll encrypt it with the server's public key and send it back over to the server. And this is the step known as the key exchange. The server then receives the pre-master secret key from the client, and it can decrypt it by using its private key to obtain the same secret. At this point, the server can then switch over and begin encrypting all messages back and forth with the client, including that same secret key, and as long as that secret key is included and the sequence numbers match up, we now have a fully encrypted communication channel. I mean, it sounds so simple, but that's really cool, and this is how everything works securely online. Let's go and actually see what that encrypted stream looks like. Go ahead and right-click Packet 19 and then go to Follow TCP Stream. And if you look inside here, you can see the initial request coming in with youtube.com, but then after the keys become exchanged, everything becomes encrypted beyond that point. That's really cool. And that's what's missing in the original HTTP request as opposed to HTTPS. So let's close that, go back to the original packets, and then we can right click where the post request occurs, follow it, click on follow HTTP stream, and check this out. You can see the password and username transmitted here completely clear to read. And this is known as clear text, as this is data that's been transmitted without any intention to be encrypted. And once upon a time, everything used HTTP without encryption. That's crazy to think about. So just remember that it's because of the three-way handshake initiating with a SYN, then a SYN ACK, then an ACK flag, that allows a client and a server to perform a key exchange process and establish encrypted transmissions that the whole world runs the way that it does on the internet today.